¿Qué pasó, mi amor?
So did you guys all get your quizzes back? Emailed them. Everybody was able to open that email.
Yep.
Very cool. I tell you what, it was like 10 times as much work as grading a paper quiz. Oh my gosh. Wow. Get the files, save the files, send the files to Notability, grade them, save them, send them back to my laptop, email them to you guys. I'm like, there's got to be an easier way. I don't know. It was interesting. Technology is something else. Song, you got your camera on.
Yeah, they finally let me have a computer, so
Oh, nice.
now you can get distracted by all the cool stuff in my room.
Oh, what do you got going on there? Interesting. Oh, what's that? Some sort of fuzzy animal. Oh, look at that. What does it say? I can't see.
Furby.
It says Sherbert.
Oh, Sherbert. He does look kind of like Sherbert.
Sherbert the Furby.
Yeah, I have more. I have one that's skinned.
Oh, no.
His fur is like behind me, along
Ever
with another Furby.
Make the lawn furry.
That's what I've been wanting to do for a while, but I don't know. Seems like a lot of effort.
Nick, what's this bomb.com thing?
Oh, I was eating earlier. And I was like,
You'll do better.
No, go check.
I don't know. Nick messaged the whole group, said from Nick Tran to everyone, bomb.com. I don't know what that is.
yeah,
it's
because I was
just-
eating like Lucky Charms, and I said it's breakfast, lunch, and dinner time all at the same time with Lucky Charms, and he said bomb.com.
Ah,
Yeah.
gotcha. That is my wife's favorite cereal of all times, Lucky Charms.
Mine is Reese's Puffs. I've never had them until like this year, like 2020, and they're really good. They rock my
You've
world.
been missing out.
Yeah, my parents are like health nuts, so.
So you never got any of that bad for you stuff growing up?
Yeah. I mean, also this year is the first time I've ever tried Lucky Charms, not like the off-brand healthy kind.
The things you experience when you go away to college. You know, most kids, yeah, I tried drugs, I tried alcohol. No, I tried Lucky Charms.
Yeah.
Very
and
good.
proceeded to get addicted.
They're good.
Atria, you've never had either one?
No, I don't know why. I've never just wanted to try either. I just have Cheerios, but the one that doesn't have honey because it's
Oh my
too
gosh,
sweet.
you eat the
I
boring
like to add my
Cheerios with
own
nothing
honey.
on them?
No,
Do you like put something on them? Honey? Or
I
maybe-
sometimes put honey, yeah, but pretty much, I don't know. I like boring food.
Wow. There he is, Mr. Gamer himself. Fired it up. Who else is going to join us via video today? Just a few of you? Hey, Raylene, how are you?
Hi.
Yeah. Looks like you guys are doing well. So have any of you like cooking and making fun food while you're home?
No.
No.
I mean, I was just eating Lucky Charms for breakfast, lunch, and dinner, so.
Like Minsung had like a juice box or something. I was gonna guess, was that a Capri Sun? I didn't even see it and I was gonna guess that. Man, I'm good. I don't even know if I've ever had one of those, but wow.
It's really good.
All right, let me share. Oh, where is it? So that's what my wife and I made on Easter Sunday.
So
Ooh.
lucky.
Yeah.
Those are good. You should bring them to class so we can all eat them.
Yeah, but we're never going to meet again.
Yeah, exactly. You should bring them to the Zoom.
They're called sfogliatella. They're Italian pastries, many layers.
I finished 10.
They're a lot of work. See, look at that. You got to roll them out, all the little layers. You make it into a funnel. You can see all the layers. So that was our fun project for the weekend, was making pastries.
Did it taste good?
Oh yeah, they're amazing. We still have some because there's just two of us eating like a dozen pastries. And then they have I don't know, it might not sound tasty to a younger palate, but it's got a ricotta cheese semolina mixture with citrus and candied citron, and they're very good. My wife discovered them in Naples, and she's wanted to try making them ever since, and that was like, I don't know, 15 years ago. So this was the first time we had time and we tried it, so it was fun. Beignets, well, they're kind of like beignets. Beignets are deep fried. These were baked, but beignets aren't bad. Beignets aren't bad. All right, it's 5:30. We can get started. How about we go through the quiz? I did not hear from anybody, so now that, let's see, I've got 32 people in class, so that's not everybody by a long shot. So either some people are just not interested in coming anymore, or they're going to come a little bit late. For the 33 of you that are there now, did any of you not get your quiz back? Or you got someone else's quiz? I hope I didn't send you someone else's quiz. All right, so having heard nothing, let me pull up the quiz itself, and then we can go through it. All right, how am I going to do this? It's the easiest way to do this. I think I need to share a copy of that quiz. All right, so let me just do this for a second.
Do you know when our exam would be?
Yeah, we could talk about that. Hold on one second.
Okay.
Also, for the homework, where should we be at with the
Very good question. So let me go back to Zoom and share my screen again, because clearly we are not where we need to be. And I was thinking about that even today, because we're not going to cover everything. I don't think we're going to be able to get through everything. And I don't want you have to worry about doing homework for things we didn't cover. So let me share my desktop. And then.
Most of my classes are behind too, so you're not the only one.
Oh, that's good to know. So right now, this is where we're at today. Today is 4:14, and we're supposed to be talking about chemical bonding, right? And we were supposed to start talking about chemical bonding last time, and we just did quantities and chemical reactions. So we just finished the chapter 8 stuff. And I see these homework and things about photoelectric effect. That's model hydrogen atom. Those are things I'm not going to have to worry about. It's just, it's important, but it's not important enough for me to continue with it. So I'm going to go back in the homework and look at the stuff that covers these things that I haven't talked about. So today we're going to talk about, we'll go through the quiz, then we'll talk about the periodic table, electron configurations, Lewis dot structures, and how it relates to bonding. We'll try to get through that stuff, because then there's group activity, which you can work on your own or as a group, that relates to those particular things. But to me, that's really, really important. I don't think we're going to get through all of that today, but we have a couple of sessions assigned for chemical bonding. We will talk more about bonding. Now, exam 3 was supposed to be set for April 16th, which of course is this Thursday. We just took quiz 3, so it looks like quiz 3, we took it on 4/9, so we're off by about a week. So I would say the earliest we're going to take exam 3 would be April 23rd. That would be the earliest. I also am hesitant to give you an exam, a quiz exam, and then a final exam all within like 2 weeks. So we're either going to have one quiz removed or one of the exams removed, just because it doesn't seem right to me to punish you with that many assessments when we could be having a class together in terms of the things that are going on. And we'll probably talk a little bit more about the final exam. The final exam is cumulative, but it may turn out that maybe we have exam 3 here, and then the final exam will be the last exam, and it will be more heavy on the recent material, but it will still be cumulative for the whole semester. And that's easy to do because sig figs, molar mass calculations, it all builds upon one another. So it's not like you have a whole lot of new things to learn, right? So I'd like to get through as much of this as possible because it's all really important, but I suspect, if anything, we're probably not going to spend as much time on solutions, even though I think solutions are important. It's not as important as bonding and some of these other things. So to reiterate, the earliest we'll have exam 3 would be April 23rd, which would be next Thursday. So not this week Thursday, but next week Thursday. So that's the earliest it would be. Okay. And the topics, again, we mentioned those. So we're not going to be talking about the topic of, well, we are going to electrons and atoms in the periodic table next. I thought there was more in here. Well, this photoelectric effect, I'm not gonna talk about that. So, and we don't do these FET exercises anyways, but I'm not gonna talk about that.
So we don't have to do homework 20 and 21.
I would have to look at homework 20 and 21, Minsung, because I'm not sure what the topics are on homework 20 and 21. I will look at those. I'll write myself a note to check the homework to get rid of. So let me write a note. Okay. Also, I believe the faculty senate at Cal State Fullerton did pass a resolution so that you guys do have the option of going to pass, no pass as the letter grade for this class. I'm pretty sure that was ratified by the faculty senate. Did any of you get an email talking about your grading options if you wanted to go to pass, no pass?
No.
No.
Nobody got any information on that, huh?
No.
I saw like a posting. Hold on. Let me go and find it.
I didn't get an email, but I got it sent to me. Like someone just forwarded it to me and they explained like what they said was going to happen.
Right.
Yeah, that's pretty much what I got.
So you'll have the option, I'm pretty sure, and I think it goes all the way to the end of the semester, so you can see what grade you're getting and then decide if you want to pass, no pass. It really doesn't matter to me. For this particular class, I suspect a lot of you are taking this class just to prep for the next chemistry class, so the grade is probably not super important to you unless you're getting an A or a B and you want to add it to your GPA. So I'm going to reserve any kind of judgment on if you want to take that. There it is, the academic Cedar posted that. So if you guys click on that link, it'll explain those things in terms of your options for the class. And I'll do whatever you want. And like I said, my grading policy will be to try to help you in any way I can to get the best possible grade. But keep in mind, this class really is about preparing you for the next class. And so it's super important to practice, right? Were there other questions?
Professor,
Yeah.
I heard if you choose like the credit or non-credit, then it will affect your financial aid.
It might. That's something that happens at Fullerton College too. If you're getting financial aid and you fall below a certain number of units, so for us it's 12 units. I don't know if it might be 15 at Cal State Fullerton. You have to check with your financial aid office. But if you fall below a certain number of units, it can affect your financial aid. And if you're getting federal financial aid, they may require you to pay that money back. I don't know explicitly because we have lots of other funding at Fullerton College. There's promise grants and there's other things that are state of California money, and all that stuff's being waived right now. There's also the option to take a W if you wanted. I don't think any of you are in that boat where you'd want to take a W, but they're extending the ability for students to take that because of this whole mess. Pearl, I see you have your hand raised.
Yeah, I was wondering if there's any way you could tell us our current grade, like how we're currently doing, because I checked online for the grades and it really doesn't show anything for your class.
Yeah, it wouldn't show anything. Probably what you would do is, so I'm looking at the piece of paper that has all the grades on it. For you guys, I have 3 quizzes and 2 exams and then homework, right? So the easiest way to figure out your grade would be to get a quiz average, get an exam average. So take your quizzes. You should have the 3 scores that you got, get an average on that. You should be able to take the exams, the 2 exams you got, get an average on that. And then your homework, right? And I believe originally the exams were worth more, but I think it amounts to something like 60% of your grade is exams. I want to say, I think 25% is quizzes and another 15%. I'd have to pull up the syllabus to look. So give me a second here. No worries, Daniela. She just has to leave early. Okay. So let me pull up the syllabus here real quick. I'll share my screen in a minute. Okay. All right. So here's the syllabus. So if we scroll down, you can all see the syllabus here. I think I'm sharing, yeah. So if we look at this, originally we were supposed to have midterms and finals. That was 60% of your grade. Quizzes were going to be 15% of your grade, and all the rest of this stuff as assigned. So sapling, we didn't ever do this activity, GA, FET business, and we didn't, I mean, participation was basically me checking you guys off and participating in class. And so what I mentioned the last time is that I think what I would do is I would just take this chunk here, so sapling, activity, and participation, which is like 25, and just take whatever your homework was and count that as that same percentage. So if you wanted to figure out your grade, you would take your exam average, and right now you only have 2 exams, right? So I would just say your exam average, 0.6 times whatever your exam average is, plus 0.15 times whatever your quiz average, plus 0.25 times whatever your homework average is. And that adds up to 100%. It should give you whatever your grade turns out to be. I can actually do that if you guys want. That would be that way, and I can just base it on the numbers that I have. But I probably would have to do that tomorrow sometime.
Yeah, appreciate that if you can.
Okay, sure. I can do that for you guys. All right. Anyone else? Cedar, were you saying something, or you're just laughing to whoever you're conversing with elsewhere? All right. Any other hands up? I don't see any other hands up.
So, Professor.
Yep.
So we decide whether we want to do pass or no pass, or
It's up to you guys. Yep. Mm-hmm.
Okay, just making sure. All right.
Yeah,
Perfect.
I think. Can I give you the link to last week's lecture? Yeah, I'll have to post it on. I totally forgot. It downloaded on my computer and I never listed it. I never put it up on YouTube. So let me make a note to myself to post last week's lecture. Post lecture. All right. Okay. Check grades. Okay, I can do that. Any other questions? I'm looking here. I don't see any other questions. All right, so let's talk about the quiz. I think I pulled it up. Let me go back to sharing my screen. Actually, you know what? How about we do it this way? I'll do the work on my iPad. Wait, nope, I think I got it figured out. Hold on. Not going to share my screen just yet. What I'm going to do here is I'm going to send this thing to my iPad. I just pick it up. All right. I'm just hesitant to do everything on my iPad just because. All right. What's that? Oh, I thought I opened up the quiz. What just happened? Didn't I have the quiz? There it is. All right. Let me see. All right. Actually, I have a quiz that somebody worked on, but that's fine. It doesn't matter. I took the name off, so it doesn't matter. All right. Let me see if I can share this. Oh, send a copy. Nope, I don't want an airdrop. Oh, man. Here we go. Accept notability. All right, here we go, boys and girls. I'm going to try this. Done. Close this. Let's share screen. Come on, you can do it. And yeah, there it is. Woohoo! All right, I'm going to turn this way. All right. So, quiz. Perform the following conversions of pressure units. 1.6 times 10 to the 5th torr equals question mark atmospheres. All right. So, the thing you got to remember for this one is that 1 ATM equals 760 torr. Right, and you could have looked that up, right, because you had your computer in front of you. So it would have been simple to say 1.6 times 10 to the 5th torr, 760 torr is 1 ATM, right? The torr cancels out, and the correct answer is D, 2.1 times 10. I'm gonna pull up my sheet here where they didn't work, okay? All right, next one. A sample of helium gas occupies 2.65 liters at 1.2. What pressure would this sample have? Would this sample exert in a 1.5 liter container? So again, looking at this, they're giving you a volume and a pressure, and it's asking you for a new pressure at some new volume. So this is basically P1 V1 equals P2 V2. And so if you want to solve for P2, right, that would be P1 V1 over, P1 V1 divided by V2 equals P2. So you just plug those numbers in. So P1 is 1.20, oh my gosh, that looks bad. 1.20 ATM. That is a point right there. 1.2 times 8 PM. That's P1. V1 was 2.65 liters. And divided by V2, the new volume is 1.50 liters. And questions like this, your answers should make sense, right? So if we're not changing the temperature, right, but we're going from 2.65 to 1.5 liters. So basically we're taking a container that's this big and going to a container that's big. So I'm decreasing the volume. Ask yourself, what should happen to the pressure? It should go up, right? So you expect to get a bigger number. And in fact, 2.65 divided by 1.5 is a number bigger than 1. So you should go up in pressure, and the answer is C, 2.12 atmospheres. Sample of helium occupies 12.4 liter at 23 and 0.9. What volume will it occupy at 40 and 0.95? So this is the same, so you don't have to do anything with that. That's just what we call superfluous information. It's just extra. It doesn't do anything. This caused a number of you a problem. What problem did you all make? What mistake? You didn't do what?
Not converting to Kelvin.
Yeah, a number of people failed to convert to Kelvin. And here's the thing, guys. If you showed me your work and you didn't convert to Kelvin, you did it with degrees Celsius, I gave you so the multiple choice were worth 2 points each. If you showed work and I could see what you did wrong, I only took 1 point off. If you didn't show work, I couldn't give you any partial credit. However, if somehow I missed your work and I took 2 points off and you had to work somewhere, make a note of it and let me know and I'll give you that point back, all right? So pay attention, look over your quiz. If you had the work and you sent it to me and somehow I failed to give you credit for your work, that was a mistake on my part, probably related to my inability to work technology, okay? So you have to...
Do we just email you about that, Professor?
Sure, yeah, you can email me about that. So if I failed to give you that credit, make sure I do that, right? So all the multiple choice were worth 2. If you showed some work and still got it wrong, I typically only took off 1 point, right? So that I could kind of see where you made a mistake, right? So in this particular case, we're kind of doing a similar thing here. We've got 12.4 liters. What volume will it occupy at 40 degrees? So we're going from 23 to 40. Temperature is going up. So what should happen to volume? Well, if temperature goes up, the volume should also go up. So I already know, right, if I start at 12.4, my answer has to be bigger than 12.4. So I already know that answer is wrong and that answer is wrong because they're both smaller than that, right? 21.6. Well, so 23 to 40 is not quite doubling, but that might seem like a reasonable answer. And I think if you plug 23 and 40 into the equation, I think that's the answer you get, but that's the wrong answer. This is the right one. So the formula we would use for this, again, is you can write out the whole formula if you want. P1V1 over T1 equals P2 V2 over T2. In this case, T1 and P1 and P2, excuse me, V1, no pressure, P1 and P2 are the same, so we could just cancel those out. So it's basically V1 over T1, so 12.4 liters over temperature 1. So 23 plus 273 is what, 300? Equals V2, which we don't know, over T2. 40 plus 273 is 40 plus, what is it, 273 and 30 is 300, 310, is that right? 310. I have to look at my page. I'm trying to do this from memory. What question are we working on? We're working on number 4. My work is somewhere around here. I think I could do those in my head. Pretty sure that I mean I know the answer is I don't know my sheet. So number 4. The answer is C, as we said for number 4. The answer is C. All right. Next one. Doing it on the wrong screen. Got too many things. I'm trying to do my computer, not the thing. All right. If the temperature of an ideal gas is raised from 100 to 200, in retrospect, I'm thinking this might have seemed like a trick question because 100 to 200, you're like, oh yeah, that's doubled. So that if you increase the temperature, you double the temperature, the volume should double. All right. That's the simple answer. But remember, this is in Celsius, not in Kelvin. Right, you got to change these to Kelvin. So it's really going from 373 to 473, which is not doubling, right? So none of these make sense except for E, none of these, all right? 4.37 gram of a certain diatomic gas, all right? So that means you got a choice of 7 species. Occupies a volume of 3 liters at 1 and temperature of 45. So this is basically PV equals nRT. And you're going to want to solve for N. So PV over RT equals N. Remember the units on N, though. Those are moles. Many of you just, well, a lot of you did some interesting things there, and I'm not 100% sure why you did some of the things you did. I tried to figure it out, but I wasn't able. So if we just plug in the values, so we've got pressure is 1 atmosphere, so we have 1 atm The volume is 3.00 liters. R is 0.08206 liter atmospheres per mole K. And temperature is 45 plus 273. That's in Kelvin. If you do the math on that, you should get something like, what do I have here? I have 0.115. 115 moles is what I get. What I get. So that's the answer to this point, 115 moles. But that's not going to tell you what gas it is. You have to find the molar mass of the gas, right? So 0.115 moles. In order to find the molar mass of the gas, you've got grams divided by that. All right. So 4.37 grams is the same thing as 0.115 mole. If you do that math, you get 38, which is the molar mass of the diatomic gas, right? Do any of these have a mass of 38? Well, the mass of fluorine is 19, and 19 times 2 is 38. So it turns out that that was fluorine. The molar mass of oxygen is 32. The molar mass of chlorine is about 71. Hydrogen is 2, and nitrogen is 28. STP, standard temperature and pressure. Typically, you'd want to express that in either Celsius or Kelvin. So 0 degrees Celsius or 273 Kelvin. Some of you put it in Fahrenheit. That's fine, I guess. And pressure is 1 atmosphere or 760 millimeters, or you could have given it in pascals if you want. 22.4 liters equals 1 mole. So if you have any gas, doesn't matter what it is, 1 mole of it at STP is 22.4 liters. An oxygen sample has a volume of 4.5 liters at 27 and 800 torr. How many grams of oxygen? So this is kind of the reverse of this question, sort of. Once again, they're giving you a pressure, a volume, and a temperature. They're asking you for grams, but this information will lead to moles. So once you have moles and you know that it's oxygen, you would use the molar mass of oxygen. So PV equals nRT. You want to solve for N, so it's again PV over RT equals N. So we have pressure. Oh, and this is, I guess, is a bit of a trick here too. I don't want to say trick, you just got to pay attention to units. R is in liter atmospheres per mole K, so torr has to be converted to atmospheres. So 800 torr, there are 760 torr for every 1 atm. So that's the pressure. The volume is times 4.50 liters divided by R, which is 0.08206, and divided by T. T is 27 plus 273, should be divided by 300K. When I did that math, I got 0.1924 moles. So this equals 0.1924 moles of oxygen. And then 1 mole of oxygen is 32 grams of oxygen. And so that should come out to about 6.2 grams of oxygen. A number of you at this point used Avogadro's number. So what you would have calculated there was you would have calculated molecules of oxygen, not grams of oxygen, which is, I know, a little bit confusing. So that was probably the most consistent error that I saw, is that people used Avogadro's number there instead of the molar mass. Convert the following word equation to a complete balance.
Wait, Professor, instead of the mass being 32, right?
Yeah, the mass is 32. If you use 16, okay. I should have only taken off 1 point.
Oh, no, I used 32. I just wanted to make sure.
Okay, yep.
All right, thank you.
Sounds like I have a very young student there.
Sorry, that's my nephew. Sorry about that.
How's he doing?
He's doing good, Josh. Tell you want to say what's up? Say hi.
Hey, what's up, bud?
Right, you gotta bring earphones on, but he's right there. Learning chemistry.
Nice. Okay. So aqueous aluminum chloride. Let's go ahead and write that particular thing out. So aqueous aluminum chloride, AlCl3, AQ. By the way, this is a legitimate exam kind of question, right? Because it covers a number of things. It covers naming, it covers formula writing, it covers balancing the equation. So realize that some of the later stuff we learned is really cumulative anyways, where you're practicing things you learned early on, right? So there may not be this whole heavy section about naming. It may be brewed into a question like this in order for you to do a much larger kind of picture, right? So aluminum chloride, right, means you got to remember aluminum's +3, chlorine is -1 to get the formula AlCl3. Sodium sulfate, so Na2SO4, SO4. This is also aqueous. And then again, this is kind of related to the thing we talked about, solubility rules, right? So this stuff is soluble, certainly because I've got a group 1 metal. This is soluble because I've got a chloride. Most chlorides were soluble. But when you mix them together, right, they can trade places. And if they do, you're going to make what we have here is solid aluminum sulfate. This is probably the one that threw most people for a loop, is they didn't write the right formula for aluminum sulfate. So aluminum is still +3. Sulfate is -2. So the formula would be Al2SO4 taken 3 times. And then you still have sodium chloride. You have to balance it, right? So in order to balance it, you've got this little issue with 2s and 3s over here, right? So you've got 2 aluminums here. We put a 2 there. Then that gives us 6 chlorine. So I have to put a 6 there. 6 sodium chlorides gives me 6 sodiums. And so there it is balanced. 2, 3, 1. This, by the way, is solid. This is aqueous. And then you have it balanced that way. So this is a double replacement or an ionic. You could also have written that it was an ionic reaction. I didn't ask you to write the ionic equation or the net ionic equation, but that would come on the exam or quiz, or on the exam we do next, right? So you'd be asked to write this expression, then break it down into the ionic equation. So if in fact we had asked that, we might as well just do it just for fun, if that's even a possibility. So if this was, if it asked you for the ionic equation next, you would break that into the ions that make it up. So you would write 2Al + 3 aqueous plus 6Cl- aqueous plus 6Na+ aqueous plus 3SO4 - 2 aqueous produces Al2SO4 3 solid. Notice I don't break that one apart at all because it's a solid, plus 6Na+ aqueous plus 6Cl plus 6Cl- aqueous, right? And then if we wanted to do the net ionic equation, we would highlight the things that are the same on both sides. So I've got Cl-, 6Cl- is here, and 6Cl- is there. Got 6Na+ is there, and 6Na+ is there. The sulfate and the aluminum are combined over here, so I can't cancel them out over there. So the net ionic would be 2Al + 3 aqueous plus 3SO4 - 2 aqueous produces Al2SO4 3 solid. So this is the overall expression, the overall equation. This is the ionic. Sorry about that. No, don't look at that. Sorry, you're not supposed to see someone else's eye. Totally screwed this pooch. Sorry. Don't even know what I was working on now. Recent.
Maybe go to, yeah, recent.
Sorry about that. This is the ionic equation. This is the net ionic equation. So I didn't ask you about those, but that would be what you would do next. And then we had this last question about the pyramid. Any of you guys know that the pyramid on the top of the Washington Monument was made out of aluminum? Yeah, I found that kind of interesting.
No,
I didn't even know there was a Washington Monument. So.
What? Wow.
Same.
Got to go to Washington, D.C. Go to the mall.
Yeah.
See all the
Right now? Let's
Have
go.
you
No,
have you ever seen the pictures of the tall
obelisk?
white built like obelisk? Yeah.
Yeah.
That's the monument.
The reflecting pool, and they talk about the cherry blossoms in the spring in Washington D.C. on the reflecting pool.
Oh yeah. Is that where the president does his speech?
It could be. Yeah, but that's the
being
Washington
inaugurated.
Monument with the reflecting pool.
If you watched Spider-Man Homecoming, I believe they use the Washington Monument as like a backdrop kind of thing in one of the scenes.
Probably green screened in something.
Oh yeah, no, yeah.
Okay.
But they reference it.
Right. So this last question, I guess I kind of feel a little bad that some of you didn't even try it, right? And that I don't know, maybe it's just a matter of practice and feeling comfortable, but remember my one admonition, when in doubt, convert to moles, and a few of you tried that, but really, if you don't know how to start a problem, you really should just say, okay, the first thing I should do is I should change grams to moles, and I've got 2 grams, why don't I just change those to moles, right? So this is a classic example of a stoichiometry where you're given grams of something, right? Ask for grams of something else, right? If you start with 225 grams of aluminum oxide, how much aluminum can you produce? If you start with 225 grams of potassium, how much aluminum can you produce, right? So really, it wasn't the simplest of questions, right? Because you have to do both of these, right? So that makes it an excess limiting, but even if you only did one, right, you would have been on the right track, right? So for any question like this, if I give you grams of something and ask you for grams of something else, it's always 3 steps. It's always 3 steps, and the first step is always to change grams of what I gave you to moles, right? So again, even if you don't really get, I don't know why I'm doing this, just this is the way I do it, this is what he taught us, right? For now, that's perfectly legitimate to just assimilate the technique and then go from there, right? So in this particular case, I would say, okay, here's the balanced equation. I know that there's a ratio of 1 to 6 to 2 to 3, but I'm interested in how many grams of aluminum I can produce. That's this guy. And I've been given amounts of this and this. So my goal is to take this and calculate grams of aluminum and take this and calculate grams of aluminum. So I have 2 things I have to do. All right, so I'm going to start with the first one, 225 grams of Al2O3. Our magic first step is, when in doubt, convert to moles. So 1 mole of Al2O3. Go to your periodic table, and if you go to your periodic table, you will find that that adds up to 101.96. All right. The second step is from the balanced equation. So for every 1 mole of Al2O3, I should get 2 moles of aluminum. By the way, there are multiple ways to do this problem, right? One of you did it in a completely different way that I did it, and I think I commented good work or something, because you understand the excess limiting and you are comfortable that you can just solve it the way you want to solve it, and I'm totally cool with that, right? Do what works for you. And then 1 mole of aluminum is, what's it, 26.98 grams of aluminum?
Yeah, Professor.
Yes.
Okay, can you show us what that student did?
Can I show you what that student did? Yes, I will. Absolutely. I'll show you what they did. I kind of remember what they did. Yep. After I'm done, I'll show you how they solved it. Okay. So if you look at what we've done here, grams of aluminum cancels, grams of aluminum oxide, moles of aluminum oxide, moles of aluminum cancel. And when I do all this math, I'm going to end up with grams of aluminum. But what this tells me is, let me just write the number down. I got 119.08. So the answer is 119.08 grams of aluminum. All right. What that tells you is that if you use up all of this, that's how much aluminum you can make, right? Notice I said if. If you use this, this is what you get. If you use this, this is what you get, right? But that's only one of the starting materials. You got to check the other starting material as well. So I also gave you 225 grams of potassium. So you got to check that guy as well. So 1 mole of potassium, was it 39? 39.10 grams of potassium. Balanced equation says that there's 6 moles of potassium for every 2 moles of aluminum. So 6 moles potassium for every 2 moles of aluminum. And then the last step is the same. 1 mole of aluminum is 26.98 grams of aluminum. And I got 51.8 grams of aluminum. Okay, so that's the other answer. So what that says, let me do a different color. What that's saying is if all of this reacted, this is how much aluminum you would make. All right. Now, the key for you guys is to recognize I gave you some of each starting material. And normally when you're given amounts of 2 or more reactants, I'm giving you extra of one of them, right? And so when you get 2 amounts, a couple of you said, oh, the answer is 119.08 plus 51.8. Well, no, because that presumes both of these things reacted completely. But keep in mind, when you mix these two together, a reaction is going to go, it's going to go, and eventually it's going to stop. And it's going to stop as soon as the limiting reagent runs out. And this is the smaller number. So that means this is the limiting reagent. So as soon as all of the potassium is used up, I made this much aluminum, the reaction stops. I do not make that many grams of aluminum, right? It just stops. And what that tells you is that at the end of the reaction, you have aluminum, you have potassium oxide, and you have aluminum oxide. There's a bunch of aluminum oxide left over. It's just sitting in the container. It just didn't react, right? And again, we do that because it forces reactions to go to completion. So when you're given amounts of 2 reactants, you have to check each of them to see how much product it makes, and then pick the smaller of the 2, all right? Now, somebody said, how did the other person do it? Okay, the way the other person did it is the other way to do an excess limiting reactant is to say, pick one and calculate the amount of the other that's needed. Okay, so let's just say I started with 225 grams of Al2O3. What I would do is I would say, okay, well, actually, there's a third way. This is not the way the other person did it. Now I remember the way the other person did it. Let me go back. I'll come back to this, but I want to go back and show you the way the other person did it. So the way the other person did it is they actually calculated moles. So they took 225 grams. I'm seeing some conversations here. Maybe I should look at this. Sorry, I'm looking at the conversation. The time on my iPod is still 9:41. I am a time traveler. You guys are having too much fun. I should not pay attention to that. All right. The way the other person did it, they took 225 grams of Al2O3 and they changed it to moles. All right. So 1 mole of Al2O3, and that's what did I say it was? 101.96, 101.96 grams of Al2O3. And they calculated that out. which I'm going to have to do on my calculator in a minute. They also started with 225 grams of potassium and said 1 mole of potassium is 39.10 grams of potassium. And they calculated, so they calculated moles of Al2O3 and they calculated moles of potassium. Let me get my calculator. I'm just going to do this math real quick.
So are you saying that you just stopped at moles and you just figured that one?
That person did, yeah. What they did is they calculated moles, but you got to look back at the balanced equation, right? So let's just do the math real quick. 225 divided by 101.96. So this is 2.206, and then 225 divided by 39.1 is 5.75 moles, okay? And so then if you look back at the balanced equation, it's 1623. So let me write that balanced equation down here. 1 Al2O3 plus 6K goes to Al solid plus K2O. 2 Al solid and 3, is that right? 3 times 2, yeah. So you looked at this, and what you see here is that for every one of these, you need 6 of these, right? And so they said, well, I know that I have to have 6 times as much potassium as I do for aluminum oxide for this to all get done. So this times 6 is about, I don't know, about 13 moles of K are needed. Do I have 13 moles of K? The answer is no, I don't have 13 moles of potassium. So they said, this is the limiting. They decided that that one was limiting just by inspection, and then went ahead and then just did the math based on this one and finished those steps, right? So there's so many ways to do excess limiting problems, right? You can compare them. You can't do it with the numbers I gave you, though. You cannot compare these numbers because this is a mole ratio. So if you don't have moles, you can look at it, you can guess, you can take your best shot, but you really have to be in moles when you're calculating ratios and looking at those particular things, right? So that would be one other way to do it. And it's perfectly logically sound. What I was going to do over here, pick one and calculate the amount of the other needed, I would have done the same thing, but I would have gone through to grams. So I would have said 225 grams of aluminum oxide, 101.96 grams of aluminum oxide. And it's not that this doesn't make sense to me, it does. But I feel like this method here on this page, how do I say this without making people feel bad? This is a higher level thinking method. And if you're not thinking at this level, I don't want to expect you to have to think at this level, all right?
And that's what I was asking last time about the moles, because that's kind of how they teach you on the homework too.
I get that. I feel bad about that because really what you're doing when you do it in that respect is it works. But in real life, nobody ever stops at moles, right? And I hesitate to have you calculate moles just for that very reason. But you can, absolutely. If it works for you, I don't want to diminish that. But I also want to make sure, because remember, a big goal of mine is to make sure that you're comfortable with and feel successful heading into the next semester. So getting the calculations right is the most important thing at this stage. Having the full concept of understanding, it's in the homework. If you practice it and get it, I think that's great, but I don't want to assume everyone's going to be able to make that leap. All right, so 1 mole. And maybe that's wrong of me. Maybe I should assume you all can do that. I don't want to diminish your abilities. I would have said that there is 1 mole of Al2O3 for every 6 moles of K. And that's actually what that was done in that particular step. If you had stopped at this point, you would have gotten moles of potassium, but then you have to go back and compare and think it out. Do I have enough? What's limiting? What's going on? 1 mole of potassium is 39.10 grams potassium. So if you did this, you'd get some number. Let me just do the math real quick. And it's the same logic. 225 divided by 101.96 times 6 times 39.1. So the answer to this is 517 grams of potassium. So what the statement is that in order to use up all of this aluminum, you need this many grams of potassium. And you got to say, do I have that many grams? I was only given 225 grams of potassium. If I needed 517 and I was given this, that means this is limiting. It runs out. But still, you haven't answered the question, right? Because the question said, how much aluminum can you make? So now you still got to go back and say, okay, this many grams of potassium can produce how many grams of aluminum? So you still have to go back and do this. You still have to go back and do this whole set of calculations here. Right? So the reason I prefer this method where you take each one and calculate them is it's fail-safe. It always works. If you do this math right, you get a number here, you get a number here, you pick the smaller number and it's the right number. And I think that to me is very important to make sure that you have a tool that if you follow it, you can be successful every single time. These you can be successful, but you have to practice a lot and you have to think long and hard about these questions, which in the end, that's what I really want. But I'm not 100% sure that's the goal of this class, is to make sure that you have the full depth of understanding, because I think there's just too much material in the class. But I could be wrong. Again, I don't want to minimize your intellectual capacity. All right, so that's the quiz. Let me stop sharing for a minute. Get to see your faces again. and read these comments about being a time traveler. I think that's probably it. Okay, I think that's when it. Yes, Raylene, when you do that, the smallest number is always the right answer, right? If you're given, if you have two reactants, you take each one and calculate the product. The smaller answer is correct. If you have three, calculate the product. The smaller one is always the right answer, right? If I only give you one reactant, well, then you only have to calculate one product, right? So the reaction is pretty straightforward that way. And so it will not be any different than that particular thing. Yes, the answer for number 12 is 51.8 grams of aluminum. That is correct. And I was pretty lenient on sig figs. I wasn't too harsh. But again, keep in mind, if you are crazy about the sig figs, if you put 10 sig figs, I am eventually going to have to take a small point off, right? There's all sorts of rooms for rounding and things like that. Chris, is that a hand up?
Yes, there's a hand up.
What's up?
Can you explain number 5 for me again?
Can I explain number 5? Sure.
Yeah, just one more time for me.
No problem.
Because I put B, but then when you were explaining that you could convert it to Kelvin,
yeah,
I thought the answer was increases by a factor of 100. But
number 5. Okay. Well,
yeah.
I guess what the easiest way to get that is to just do the math. All right. Okay. So let me come back. Oh, I have to share my screen. Sorry. Just stop worrying about my new iPad. Number 5. Oh, I got to turn my pen back on too. So many technology things. Okay. So if the temperature of an ideal gas, okay, it's just an ideal gas, it's just some gas, is raised from 100 to 200 while the pressure remains constant, the volume will. So the way to do this is just pick some volume. So let's just say I have 1 liter. And I'm changing the temperature. All right, so actually, let me write the formula out first so we know which what we're using. All right, so it's temperature that's changing, and we're dealing with temperature and volume, right? So I always write the full expression out. I'm going to go to the bottom where I have a blank page. So it's 100 to 200. So I always just go P1 V1 over T1 equals P2 V2 over T2. All right. And So it's going from 100 to 200 degrees C, correct? Which is 373 Kelvin to 473 Kelvin. And it's asking you what's happening to volume, right? So we don't care about pressure. So this is basically V1 over T1 equals V2 over T2. And I want to know what V2 is given some V1. It didn't give me a V1, so I can pick any number I want. So I'm just going to pick V1 equal to 1 liter. I'm just making up a number because it's asking, you know, there's a double, a triple, whatever. So you just have, all right. So want to solve for V2. So that's, this comes over here, right? So V1 T2 over T1 equals V2. And so 1 liter times 473 over 373. Let's just do that math. 473 divided by 373 is 1.26. So this ratio is 1.26, which is not doubles. It's not any of the choices you were given. So if you go back and
I see. Okay.
Yeah, does that make sense?
Yeah, that makes sense. All right. I thought they were directly related for some reason, but now it makes more sense now.
Yeah, the problem, and this is the kinds of things that I think, again, you could argue, say, you know what, Dr. Hartmann, that's a trick question. I don't like that question. But in reality, it's not a trick question because most people write temperatures in degrees Celsius, right? They don't use Kelvin. Have you ever used a Kelvin thermometer?
Never.
No. I don't think I've ever seen a thermometer graduated in Kelvin either. And so it seems legitimate to ask the question in Celsius when really what I'm gauging is, do you remember it needs to be in Kelvin? The thing I feel bad about is that basically question number 3 and question number 5 seem to be assessing the same thing, right? If you didn't convert this to Kelvin, you got the wrong answer. And if you didn't convert this to Kelvin, you got the wrong answer. So, I mean, you could legitimately say, you know what, Dr. Hartmann, that was the same question twice. I don't think that was fair. I want a point back. If you made that argument, I'd probably give you the point back.
Okay. All right. Thank you. Thank you. Yeah, again, that makes more sense now.
Yeah, I don't want to, I try purposefully not to ask the same question multiple ways, right? Thinking, oh yeah, I got him on one. I'm going to try to get him on another question. That's really not my goal in assessment. You know, although it sounds kind of fun, it's really not. It's not fair, and it's not the right way to assess students. So, any other questions out there in screen share land? I don't see any other hands. Seeing no other hands. So you guys staying home and not going out or doing anything? Everybody staying home? Min-Sung, you staying home?
Yeah. Doing assignments.
Yeah.
Assignments, exam assignments, quiz assignments.
All your other classes. I have to admit, I have gone out a couple times. I found a truck that I've been looking for a long time.
What kind of truck?
It's a 97 Dodge with the 5.9 liter Cummins turbo diesel.
Damn! Yeah. What you gonna be pulling with that?
Well, I got it cheap because it died while he was driving, and so something happened. But for the price, even if I have to buy a whole reman engine or rebuild it myself, it was so totally worth it. So
nice.
Yeah, well, if you know any, I don't know if any of you guys are gearheads out there, but the 97 and older diesels don't have to do smog. So I mean, for cars it's 75 and older. For diesels it's 97 and older. So that's the last year where you can do pretty much anything in your truck that you want and not have to worry about it passing emissions. Yeah.
Nice.
And that Cummins is like the most sought after engine. That year from 94 to, I want to say from 94 to 98 and a half, it had what's called the P pump. It's a Bosch inline injection pump. It's like super, super highly desirable. Everybody wants those who wants that Cummins truck. And so I'm like, me included. I probably have been after one for like 20 years, and I finally decided that the price was cheap enough that I'm going to buy it. And you know what? My wife wasn't even mad at me. It was amazing. She knows she'll roll down the window in her car and say, "Hey, is that a Cummins? I recognize that noise." So,
Professor, what year did you say it was?
it's a 97.
97.
Yeah, 97 Cummins Dodge 2500. So it's a Dodge Ram extended cab. It's only 2-wheel drive, though. I would have loved 4-wheel drive, but it's California. I don't need 4-wheel drive, probably. So, all right. Any other questions? If not, we can move on to some new stuff. I don't see any questions. 6:30, so we got about an hour, so that seems legit. Okay. Let me go to a new note. About that. Oh man, I just figured that out. All right. So I got to share my screen. All right. Somebody's sharing their music. Okay. So we're going to be talking about bonding next. And my guess is that you remember we've talked about two kinds of bonding so far. We've talked about ionic bonding and covalent bonding. You guys all remember this stuff vaguely? Yes? No? I can only see Minsung. He's the only face I can see. Minsung, do you remember this stuff?
I do.
Okay, good.
I remember this stuff.
Okay.
What?
The problem is that when I share my screen, I get a little view of you guys over on the side, and I don't get to see everybody who has their. I wonder if I can make this. Let me see. Hold on a sec. I'm gonna. No, I don't want that. I want to try and maximize how much of you guys that I can see. It's weird not seeing anybody. This is like that. Honestly, that's the worst part of this class, doing this thing Zoom, is I cannot look at all your faces and interact with you. It's driving me nuts. Okay, so ionic bonding, you remember ionic bonding, we gain or lose electrons. We form ions, and then they attract. That's ionic bonding in a nutshell. You gain or lose electrons. Covalent bonding is even easier. You just share electrons. What we really didn't talk about is we didn't talk about the underlying reasons for why those things happen. And we didn't talk about the underlying reasons about how we can make predictions about what's going to form, right? Why is sodium, for instance, +1? Why is calcium typically +2, right? So in order to understand that, what we really have to spend some time talking about the electronic nature of the atom. All right. That's actually at the heart of all of this stuff is now, what do we mean by the electronic nature of the atom? And we spent some time talking about the atom. So if you remember, we talked about an atom. It has a nucleus, which is positive, and then it has electrons, which are negative, right? And in an atom, the plus charges equal to negative charges. In an ion, the plus charges do not equal the negative charges, right? We also talked about the fact that the nucleus contains protons and neutrons. Right? We talked about that fact. We didn't really talk highly about why the neutrons are there, and I'm just going to briefly point out to you. Maybe we did, I don't remember. So if you remember, protons are positive. So if we've got a bunch of positive charged particles in the nucleus, like charges repel each other. That nucleus is extremely unstable. It's going to want to fly apart. And the reason it doesn't fly apart is because you have neutrons in there. And you might say, well, how does that work? Isn't a neutron a zero charged particle? Well, in reality, a neutron is an electron plus a proton plus some energy. All right, so if you hit a neutron with a big enough hammer, you break it into an electron and a proton and some energy comes out, right? And what's constantly happening in the nucleus is these neutrons are flipping back and forth between these particles, right? Such that at any given point in time, you might have these guys visible, right? Which means that there's some negative charges and there's some positive charges. And so if you've got any of this happening in the nucleus, it can act like a glue and help hold that nucleus together, right? So the reason the neutrons are there is that they help hold the nucleus together, and that's really all you need to worry about. They also give the atom its mass. They allow for things like isotopes. So remember, an isotope is where you have the same number of protons and electrons. Did I say that correctly? Same number of protons and electrons, but different numbers of neutrons. So just remember something like this. We had 1, 1H, 2, 1H, 3, 1H. These are all isotopes, right? They're hydrogen, and that's because of this number right here. So the atomic number is always 1. It's always hydrogen. But some of them have 0 neutrons, some of them have 1 neutron, some of them have 2 neutrons. So those are isotopes. They all behave the same chemically, but if we were going to do some nuclear reactions, they would behave differently, right? And so we spent some time talking about how this is related to the periodic table. So remember the periodic table in all of its glory. And by now you should be relatively good at just making rough sketches of the periodic table. The periodic table is designed, it's set up to help us understand the behavior of the atom in a couple of different ways, right? And there's a bunch of ways I could go into this. I could talk about the historical perspective of how all these things were discovered. But what I find is most useful is to look at the periodic table and help you guys understand why it looks the way it does and the kinds of pieces of information we can get from it, and then go back to talk a little bit more about the atom, all right? So you may recall that when we put things in here, so well, let's just start hydrogen, and we'll put helium over here, and then lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, right? So you might remember some of those things. So lithium, sodium, potassium, excuse me, sodium, not potassium. Who remembers what's after sodium? It's not potassium. Potassium.
Magnesium, maybe?
Yeah, sodium, magnesium, right? And then over here we've got, right, remember what happens here? Aluminum, silicon. What's under nitrogen? Phosphorus, sulfur, chlorine. Sulfur, did I just put SU for sulfur? So under nitrogen is phosphorus, under oxygen is sulfur, under fluorine is chlorine, under neon, argon, right? That's enough for now, right? So you kind of remember the general setup of the periodic table, and you might also remember that there's numbers associated with these, right? Hydrogen is element number 1, helium is element number 2. I drew my picture, unfortunately, poorly, so let me change colors and I can put it in there. So this is 3, this is 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, right? So those numbers, right, represent the atomic number, all right? So this is the atomic number, which is still the number of protons, but because it's an atom, it's also equal to the number of electrons, right? So that's useful. So what we're beginning to see here on the periodic table is the number of that element tells me something about what's happening in the nucleus, but what's also happening in the electron cloud around it, at least in terms of numbers, right? The number of electrons, right? You may not quite fully grasp Now, why does it go like this? Why is it 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12? Why does it look the way it does as opposed to just going, why isn't it just a nice even box? Why doesn't it go like this? Why is it broken apart into these pieces? And the reason it's broken apart into these pieces has to do with things that we necessarily haven't learned about yet, but I'm going to give you some terminology that's going to come up later, right? So this box, this box that I'm highlighting in this lovely pink color is what we call the S block. You may know what that means for now, but I'm just going to throw it out there because it's going to come back later and help us understand some things. And this, again, I'm going to highlight in this lovely fluorescent green color. By the way, I need to fix something as well here. Let me erase. I didn't want that color there. That actually has to be pink, right? Because helium is really supposed to be right above beryllium. The reason it's over here on the right-hand side has to do with its chemical properties rather than the number of electrons it has. So this thing that I've highlighted in green, this lovely green color, anybody know what that's called?
P.
Yep, it's called the P block. All right, we've got a few more to highlight. Let's pick blue. So this region right here, oh, my pen. That's called the D block. And then down here at the bottom, we'll make it, okay, somebody nailed it. Was that you, Minsung?
Yep.
Sheesh. Why are you taking this class?
Because I have to.
This is called the F block, not to be confused with the F bomb. My former chemistry colleague back when I lived in New York used to drop the F bomb all the time. He got away with that, I don't know. But anyways, F block, all right? And these letters designations, by the way, these letter designations aren't just something that somebody came up with. They're related to the spectroscopy of the hydrogen atom. So we're not going to do it in this class, but you might have seen it in a previous class, or you might see it in the next chemistry class you take. If you take a light bulb and you pass the light through a prism, you know that it spreads out to give you a rainbow, right? The IV. If you take an individual element and put it in a glass tube, I'm trying to draw that glass tube right now. If you take an individual element and put it in a glass tube, so let's say there's H2 gas in here, and then you put high voltage electricity through that, it will also give off light. For hydrogen, it happens to be kind of a lavender color. I can actually mimic that color pretty well. It actually happens to be this color, but maybe not that intense. Might be more like that, right? So this is giving off this lavender color light. And if you take that same lavender light and pass it through a prism, you don't get Roy G. Biv, you get a few colors of light. All right, so you might get, all right, don't hold me to it, right, because I'm just trying to create this, but you get what's called a bright line spectrum, right? Every element has its own characteristic spectrum, and so we can identify elements by that. But because hydrogen is the simplest element, it only has one electron and one proton, it has very, very easy electronics to study. And because the original study of the atoms was based on hydrogen, the person who did it named these lines, right? And they called some of them simple primary diffuse, and fine. And that's where these letters S, D, and F came from. S, P, D, and F. It relates to this block. But what it also relates to is, so we just talked about the electrons being out here in this picture. We didn't talk about how they're moving. And we didn't talk about the fact that, hey, these electrons, they're negatively charged. Why don't they just get sucked into the nucleus? The nucleus is positive. Shouldn't this electron just get, opposites attract? Shouldn't that? The answer is yes. How do you prevent this from getting attracted to this? Well, how come the moon doesn't collapse into the Earth? Anybody know? The Earth has got a very large gravitational pull on the moon. It's pulling on the moon all the time. Why doesn't the moon get sucked into the Earth? I saw some chat. I don't know, did somebody put an answer out there? I can't see the chat right now for some reason.
Nicholas said push.
Oh. The reason it doesn't get in is because it's orbiting the Earth. The reason the moon doesn't fall is because it's moving. It's constantly moving. The gravity, the reason it's going in the, well, it's not in a circle, it's kind of elliptical in its orbit, but the reason the Earth doesn't get sucked into the sun, the reason the planets don't get sucked into the sun is because they're moving. The reason satellites don't fall down to Earth, well, eventually they will, but the reason they don't is because they're moving. They're constantly moving. And the same is true with electrons. Why don't electrons get pulled into the nucleus? They don't get pulled in because they're moving, right?
Is that what you call the escape velocity?
Yeah, absolutely. Well, the escape velocity is well, actually two things. Escape velocity is what's required to escape the Earth's gravitational pull. So a rocket has to have a certain speed to be able to escape gravity and then end up outside of the gravitational pull. Once it's outside there and starts to move, I don't remember what that's called. One of my physics professors is a Raytheon guy, and he knows all about those satellite things. But escape velocity is just getting out of Earth's gravity.
Dr. Hartmann?
Yes?
So is this like PowerPoint 19?
It might be related to that. I'll pull that PowerPoint up in a minute, but I feel like I rely on those PowerPoints too much, and I say stuff that the PowerPoints say things that aren't important to me. So I'll pull it up and we'll go through it. All right. So anyways, how is this related or to the periodic table, and why do we care about it in terms of the atoms? Well, let's just write down those first atoms as we go through them. So we've got hydrogen, helium, lithium, beryllium. It wants me to hold my pen sideways. Boron, carbon, nitrogen, oxygen, fluorine, neon. Hydrogen has 1 electron, helium has 2, lithium has 3, beryllium has 4, boron has 5, carbon has 6, nitrogen has 7, oxygen has 8, fluorine has 9, neon has 10. Number of electrons. Okay, now think about this for a minute. If you've got a nucleus here, a positive nucleus, and you've got an electron that has to be moving, okay, no problem. I can put 1 electron out there and I can make it move. How does it move? Well, does it orbit the nucleus? No. It does not orbit. Does not orbit. All right. So you guys have seen this model of the atom. This picture here looks like this. Yeah, that is wrong. Okay, I know everybody uses that picture of the atom and it looks really cool, and don't get me wrong, I like it. It looks cool. It makes people think you're smart and all that other stuff. The answer is we don't know how electrons are moving. We do not know. Right? We know they're moving, but we don't know how they're moving. Right? Right? And you might say to yourself, well, how can we not know how they're moving? How can we know they're moving, but we don't know how they're moving? Well, we can make observations that tell us they're moving. All right. So for instance, if you take an electron or an atom with a charge and you pass it through a magnetic field, it curves. So we know that that electron is moving. All right. But the problem is that we can't observe them. Why can't we observe them? They're really, 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 really tiny. All right. And because electrons are are really small, all right, we're in something called the quantum world, all right? And in the quantum world, things don't behave the way they do in your world. You live in the macroscopic world, the big world. Things behave like you expect them. If you throw a ball, you expect it to travel in a curved path and hit the ground. In the quantum world, they don't behave the way you expect them to. And in fact, if you observe an electron, you change its path. All right. This is a result of the fact that when we observe it, we're usually observing it by adding some energy to it. Right. So like when you observe an object moving, like let's say you're playing baseball with your friend, they throw the ball to you, you kind of know where to catch that ball because you can see it, your brain calculates where it's going to be, you put your hand there and you catch it, right? And the reason you can see it is light from the sun or the stadium lighting is bouncing off the baseball. It's hitting your eyes. It's continuously doing that. And so you're continuously observing it. You know where it is. You can track it. The problem is in the quantum world, if we were going to look at an electron, we would have to look at it by bouncing some energy off of it. And because it's so small, any energy we bounce off of it changes the path that it was taking. So you can imagine if an electron is moving in this path and you look at it, the way you look at it is by bouncing some energy off of it, right? And it comes to your eye and you see it. The electron's not moving on that path anymore. It's moving on some entirely different path. So anytime you observe it, you change it. All right. It's called it's related to the Pauli exclusion principle. It's not really critical that you know that. What's important is that you know that they're moving. We just don't know how they're moving. Right. We just can't do it. All right. What we also know is that as you get bigger and bigger atoms, you're continuously adding more electrons to them. And so you have to ask yourself the question, if I've got a bigger atom, where am I going to put those electrons, right? And so the model that was predicted and the model that we use to describe atoms now is pretty straightforward, all right? The model for the atom is pretty straightforward. We start with the nucleus, right? And we imagine that there are these things called energy levels around the nucleus. Now, again, I'm going to draw these as circles, and this is going to look like a target, but it's just a model. It's not a very good picture, right? And so here we have the nucleus. It's only a two-dimensional picture, so it's actually not very good. And as you move out from the nucleus, we add electrons to it, right? So there's one electron. This is an example of hydrogen. It's got one proton and one electron. If I wanted to add more protons and electrons, all right, so there's another proton and another electron. Now I'm at helium, 2 protons, 2 electrons. I'm not going to worry about the neutrons because they don't really take part in any of the chemistry. If I add another, now I've got 3 particles in the nucleus. I've got another electron. And you might say, well, why don't I just put that electron here? And you could, except what we found by studying the atom is that that doesn't happen. Right? If you want to put another electron into the atom, it goes here. All right? Now look back at what we drew for the periodic table and see if this might make sense to you. Hydrogen and helium, right, are in the same place, right? Helium is really effectively here. So turn my pen off, sorry. Helium is really effectively right here, but we put it over there because of its chemical properties. So element number 1, 1 proton, 1 electron. Element number 2, 2 protons, 2 electrons. Element number 3, notice element number 3 is in a new place, right? And notice when I drew the picture down here, I did that. We had 1 proton, 1 electron, 2 protons, 2 electrons, 3 protons. I had to put that 3rd electron in the next level up. I didn't just make that up. It looks like I just made it up, but this is a result of the way atoms behave in the real world, all right? So what we find is that we build up an atom from the nucleus first, we can put as many protons as we want in the nucleus. They just all love to cram together in the nucleus. But electrons, not so much. They hate each other, and they got to stay away from each other, right? But what you'll notice is that as I move out from the nucleus, I'm able to put more electrons in an energy level. So let's go back to this periodic table, right? How many electrons do you think I can put in that second energy level? If I could put 1, 2 in the first energy level, how far do I have to go before I get to the next energy level? I have 1, 2, 3, 4, 5, 6, 7, 8, right? So that's telling me that the second energy level, right? And again, the periodic table is not a coincidence. It's built to describe the reality of what's happening inside the atom, all right? And by the way, when Mendeleev created his periodic table, he had no idea what was going on, right? But the second energy level can hold 2, 3, 4, 5, 6, 7, 8. It can hold 8 electrons. It doesn't have to hold 8 electrons, but it can hold 8, all right? We go back to our periodic table. Now we're in the third energy level, right? And life is going to get complicated here pretty quickly. And we'll talk about that in a minute. So if you go across the third one, it looks like it's the same length across. If you look at it, it looks like it's 1, 2, 3, 4, 5, 6, 7, 8. It looks like it's 8 across. Yes. But what you may not notice is that this is directly in line with that, right? I didn't draw my periodic table very well. So if you pull up a real periodic table, right, you might see some things that are happening in here. It's close. It may not be directly in line with it. It actually might be slightly down. There's an explanation for that, and that's what I'm going to get to when we talk a little bit more in depth. All right. So the reason electrons feel the way they do has to do with underlying realities within the atom. In the quantum model of the atom, electrons hate each other, they want to avoid each other, and they want to stay as far away from each other as possible. All right. And when you put electrons in the nucleus, or when you put electrons in the atom, you start at the nucleus and you move your way out, right? And then you build up the atom. By the way, this is called the Aufbau principle. Aufbau is German for build up, right? So we build up atoms from the inside out, and then we add successive electrons, and we have to put them in certain places, all right? What are these things called? Well, these things are called energy levels. Energy levels. So this is energy, by the way, energy levels to make your life fun are symbolized by the letter N, like moles, right? In the PV equals nRT are reusing letters. And so we would call this N equals 1. I'll put an arrow on there. This is N equals 2. This is N equals 3. This is N equals 4. And in reality, you can have an infinite number of energy levels. In reality, we don't. We don't have an infinite, because the atoms end at about 120, 115 elements, electrons. And so you don't have an infinite number of energy levels that you can put in. But what's true is that any electrons in the first energy level all have the same energy. Any electrons in the second energy level all have the same energy. Any electrons in the third energy level would all have the same energy. Okay. There's a couple other terms that we should probably throw out that are going to be related to the topic, which is chemical bonding. All right. And that is that the outermost energy level is called the valence shell. Right? Valence shell, right? And we've used that term, you've probably run across the term slightly when we were talking about ions, because you might say, you might have run the term like Elements in group 1 all have the same valence. They're all +1. Or the elements in group 2 all have the same valence. They're +2. So valence really refers to essentially something about that outer energy level, right? And then you might say, well, why don't I care about the inner energy level? It's really only these outer electrons that influence the chemistry of the atom, right? It's very difficult to penetrate into inner electrons, and chemical reactions aren't energetic enough to do that. So we typically don't worry about the inner electrons. And it might also be interesting for you, again, to think about the periodic table. These guys here are at the end of an energy level. So what does that tell you about their status in terms of number of electrons? These guys are all full, right? Anyone that resides in this last column has a full valence shell. The electrons are full, which means they don't want to take any more and they don't want to give any more up. And that's particularly why these guys are very, very, very unreactive. In fact, there are no known compounds of helium, no compounds of neon, no compounds of argon. None. There's never been a compound made of those guys because they just don't want to react. Okay? All right. So we put electrons into an atom, all right, and we put them in energy levels. There's some more complexity that is impossible to guess about, right? There's no way that you, looking at an atom, would say, oh, you know what? I think there's more complexity here. It's not there. You wouldn't predict it. And so let's go back to the periodic table again and ask ourselves this question, right? If this is the second energy level here, so let me pick on the second energy level again. If this is the second energy level right here, and this is the second energy level right here, why are some of them in what we call the S block, and why are some of them in what we call the P block, right? It's all the second energy level. These are all the second energy level, but some are in what we call an S block, and some are what we call a P block, right? Why is that? Well, first of all, remember this. It might not be easy to see.
Because they're at different orbitals.
Okay, you got the answer because you know some things, but is there a reason why they should be? No, there's not. In real life, anything in the second energy level is all at the same energy. Why do we have some in what we call S orbitals and some in P orbitals? The result is how the atoms behave electronically. It's not something we predict. It has to do with the fact that electrons and really tiny particles can behave like particles, or they can behave like waves. And waves can interfere and they can create things called standing waves. It's just a fact of nature, right? The analogy I guess you could make is that you might think about like addresses and where people live, right? They might all live in the same neighborhood, but some of them live in different houses. And if a builder developed a certain neighborhood, he might have, 2 or 3 different model homes that he builds. And so there might be 100 of one home, 100 of another home. You go into someone's house, your neighbor's house, it looks pretty much just like yours. You may be different paint or different wall coverings, but it's still the same house, right? And that's kind of what's happening with atoms, all right? So if we go back to our picture of the atom and we start at the nucleus, all right, keep in mind the nucleus is, I hate to say this, not important for bonding. It's not saying it's not important, it's just not important for bonding. So all the stuff we're going to talk about for bonding, you can completely ignore what's going on in the nucleus. Doesn't matter at all. I guess the only thing that matters is that it's there to generate positive charge if you start pulling electrons away, right? So if you have a hydrogen and you take the electron away, it's going to be H plus because of the nucleus. So, but it doesn't really do anything in the bonding, right? Then as you move out, and I draw these in circles, but they're really not circles. They're some shape which is designed by nature, but it's not a circle. You encounter energy levels. So this is the first energy level, N equals 1. If you look back at our periodic table, in the first energy level, all you had was the S block. In the second energy level, you have the S and the P block. So if I go back to this picture, N equals 1, you can only have S. You only have S. And when we get to N equals 2, you can have S and P. Right? And at this point, you're like, okay, I can have that. I don't know what that means, but I can have that, right? Well, we'll get there. In the third energy level, when N equals 3, you can have S, you can have P, and you can have D. And in the fourth energy level, when N equals 4, you can have S, P, D, and F. Right? So I threw that out there. That probably doesn't make a whole heck of a lot of sense to you, but what we're getting at is regions where you can put electrons, right? The bigger the atom is, the more space you have to put electrons. It's just like that. You know, if you have a small family, you need a small house. If you got a big family, it's helpful to have a big house, and you put people in different places, and that's kind of what's happening with the atom. If you've got a small atom, you don't need that much room to put electrons in. If you've got a big atom, you got to find some place to put those electrons, okay? And the way we use the periodic table, and now it's going to be useful to actually look at a real periodic table. So let me stop sharing my screen and let me go to the page for the course, and we'll look at, oh man, did I not open the course page? You know what? I'm just going to pull a periodic table from the internet. We're not going to worry about that. Just pull up a periodic table. Periodic table, yeah. I guess I could have kept sharing my screen. I didn't have to turn the screen sharing off. Let me share my screen again, but this time I'm going to share my desktop. Okay, so let's just pick a nice periodic table, one that looks relatively pretty. Okay, so there's a periodic table. That's a legitimate periodic table. All right, let me make it a little bit bigger. Okay. Okay, so if you look at this particular periodic table, which is now on my laptop, so I can't write on it, you'll notice hydrogen and helium, group 1. You'll notice numbers along the left-hand side of the periodic table. Those are important numbers. Those are N. So the numbers on the left-hand side correspond to energy levels. So what energy level does the valence electrons exist in, right? That's all. The periodic table is really all about valence electrons. Where do you find the valence electrons? As you go from left to right, what you're doing is you're filling in that particular energy level, right? And as you move around in the periodic table, you're filling in various blocks of the periodic table, all right? The one thing I want to point out to you, though, is there a question? The one thing I want to point out to you, actually, let me see if I can share this with my iPad, because I actually want to write on it. It's probably not going to let me share it.
Well, you could always screenshot on your iPad and just copy it onto your notebook.
Oh man, you smarty pants. So many things that I don't know about. How do I do a screenshot? Is there a camera on my app? Oh, there's a camera. Look at that. Allow while using the app. Oh.
You're using a Mac, right?
I am.
So then it would be, I think it's Command P.
Up, I just found it. So I got the photo. All right, so let me.
And then save as PDF file.
Gotcha. All right, so here we go. Share screen, iPad. Come on, baby. There it is. Let me see if I can mark this thing up. Notability. I'm like learning stuff right here in front of you guys. So let's go to Notability. Let's go to here. No, where's the one I just did? Why didn't it not? Huh. Wait.
Usually I just access the internet on my iPad, snap the picture, and then copy it onto Notability.
You guys are just too smart for me. There, no. Usually you access the internet on your iPad. Okay, I could do that. All right, so let's see. How about that one? Walmart. Notability. Send the Notability. It's probably going to send that whole Walmart page. Sorry. Oh, sheesh. Doesn't like me. I am sorry, guys. I am just not Mr. Technology.
You can screenshot kind of like if it's your phone, where you hold the home button and the lock button, it'll snap a picture of your screen.
Let me find a periodic table that'll actually take up my whole screen. Yeah, but you know what? That looks crappy when I expand it like that. I thought I sent it to myself. What happened? I thought I'd sent it to Notability and I didn't. Oh, well, you know what? I'm just making life complicated here. I'll just stick with my desktop. I'll try it next time. Sorry. Share screen. No, go away. All right. Anyways, so you can see this. I won't be able to point it out, but notice on the left-hand side, the numbers are going up. Those represent the energy levels. And again, when we're looking at the periodic table, it tells you a whole bunch of information. But when you're thinking about this electronic stuff, you're really thinking about valence electrons. So group 1, hydrogen, lithium, sodium, potassium, they all have one valence electron, which means that their outermost energy level, doesn't matter if it's 1, 2, 3, 4, 5, 6, or 7, has one electron in it, right? Hydrogen only has one electron. Lithium's got 3 electrons, so it's got 2 in the inner shell, 1 in the outer shell. Sodium's got 11 electrons, so it's got something a little more complicated than that, right? It's got 2 in the inner shell, then it's got 8 in the next shell, then it's got 1 in the outer shell. And we'll talk about how you can figure that out. But when you're looking at the periodic table, you're really only looking at the outer shell, which is the valence, which tells you about how those particular things behave. All right. So this thing in the middle, this that starts with the light green element number 21, scandium. So scandium 21 to zinc number 30, down to 112, back to 89. That's what we call the D block. All right. And then 5 through 10 down to 118 and 113. So that block that's got orange and pink and green and white, that's the P block. Okay. And then down at the bottom, we've got the F block, which is that kind of greenish and the blue color. Right. And the thing that's problematic when you're using the periodic table is that the energy levels don't line up perfectly. All right, and I'll draw this on the notes that we were working on in a minute, and I'll do my picture of the periodic table a little bit better this time. All right, so if I was doing my periodic table, and I'm going to try to make this look as similar as possible. I'm not going to put everything in, but as much as I can to help you understand what's going on here. You'll notice that that lines up with that. All right. So the S block over here, this is 1, 2, 3, 4, and it continues on going down. Let me just put this line across here.
I can't see what you're doing.
Oh, of course you can't see what I'm doing because I'm not sharing. Thank you. Somebody should have told me that much sooner. Hey, what are you doing? Share your laptop. Your iPad. Sorry about that. Okay. I apologize. I could see it. I didn't think about y'all. So let me rewrite this because it makes no sense if I just talk about it, talk through it. Okay. So if we redraw the periodic table and we try to show a little bit more care in the way we draw it, if my pen would draw. All right, so 1, 2, 3, 4, 5. And actually, it's probably better that we do it this way together because then you're writing it and maybe drawing it, and it'll perhaps stick a little bit better in your brain. What's kind of important is that, so the S, this is all S, what we call the S block. And this guy over here being the P block. But you'll notice that where they line up here, right? So this is the second energy level. This is the second energy level as well. Let me put these lines all the way down. So boron, carbon, nitrogen. Actually, I gotta put an extra line in there. Okay. Then the third one, right? You'll notice the third one goes over here. This guy, the D block, doesn't start until here, right? So that the start of this guy, where we had scandium right here, seems to be in number 4. But if you remember, a while back, we said, let me just go back. I'm going to try and find where I wrote it. No, I don't want you. Stop. All right. I have no idea what I just did here. Okay, sorry. I'm just like totally out of understanding what I did there. Okay, so if you remember this screen, we said that in the first energy level, you can only have S. In the second energy level, you can have S and P. So if we were looking at that periodic table I was drawing a minute ago, in the first energy level, you only have S. In the second energy level, you have S and P. And I apologize, you can't probably see that color. In the second energy level, you have S and P. That's even a worse color. In the second energy level, you have S and P. Then if you go back to what I said, in the third energy level, you have S, P, and D. Well, let's look at that for a minute. In this third energy level, I've got S, I've got P, but the D doesn't start till down a little bit more, right? Well, that's kind of a conundrum in the way atoms are built up. And I'll explain that to you here briefly. So when we're putting electrons in atoms, it turns out that, yep, we go from the first energy level to the second energy level to the third energy level, right? And we put electrons in the 1s, then we go to the 2s, then we go to the 2p, then we go to the 3s, and you think we go to 3p, which we do, then you think we go to the 3d, but it turns out that 4s is just a little bit lower in energy. Who'd have thunk? So what it turns out is that in real life, this 4s gets electrons before the d orbitals. So this really is the third column when it comes to the d electrons. Even though it's after number 4, we know that the d electrons start in the third energy level. So there's a little bit of a mismatch that you kind of have to know, right? So that this row right here is really the 3D. And that would mean that this is the 4D and this is the 5D. They're off a little bit. So these numbers over here on the left, you can really only trust those numbers for the S and the P, right? It's the way the periodic table works, and the periodic table is based on reality, not on the model. So when we really studied the atoms and you put one electron in, see where does it go? Add another proton, add another electron. Where does it go? When you go to the periodic table and when you get to this element right here, if you add one more proton and one more electron, you would think, oh, from 3p it should go to 3d. It doesn't. It goes to 4s because that's how nature likes it, right? So there's a little bit of a mismatch, but we know that, and we can use the periodic table to our advantage as long as we know that. And the same is going to be true when we get down to the F block, right? You would think, based on what I said earlier, that you can have Fs in the 4th energy level, and that is true. But if you look at a real periodic table, and I don't know if I had a periodic table up or not. Let me see if I still had one up. I do. Let me pick this one. Let's see if it'll actually give me the... My internet connection is stable enough. Oh, finally an image. All right. You'll notice, will it let me send this to Notability? How about we just copy it? Okay. Do you guys think that I could actually paste this in Notability? I'm going to try.
Yes, you can. So hit the little scissors.
Yep.
And then click on the iPad. It should say.
Oh my gosh.
You got to copy the other one.
That's it. How do I, let me make it bigger. That's good. I don't care if it's bigger or smaller. I just want it here. This will work. Oh. Thank you guys. You like totally schooled me. All right. Let's just move this up. Oh God, I copied that. That's not the one I want. Well, anyways, we can see it here down at the bottom. See this? This is the first element in the F block. See, its element is number 58. Y'all see that? So 58 should come after what? It should come after 57. That's row 6. So we're starting to get kind of weird what's happening here. In most of the periodic table, it's easy. 1, 2, 3, 4, 5, 6, 7, 8, 11, 12, 13, 14, 15 through 18, 19, 20. Everything's really easy. I'm just going across the periodic table, adding one proton, one electron. But down here, go here, then I got to go down here afterwards. And this is row 6. So I'm adding electrons in the 6th energy level here, and then all of a sudden I switch over to the F, which is in the 4th energy level. There's a little bit again of a mismatch, and that has to do with when atoms get big, they get fuzzy. And it turns out that even though it's got a higher energy number, it's slightly lower in energy, so it doesn't fill in the same order you would think, but it still fills. Okay, and so that means that on this periodic table that we had down here, if we drew the F orbitals down here at the bottom, this is really 4F, and this is 5F. Even though this guy, as we saw a minute ago, doesn't fill until after. Oh, sorry about that. What size point I was using that? So this will be 4. Oh, it's a little too big. So this is 5. This is 6. So we fill this guy. We fill this guy. We fill one of these guys, and then we go down here and start filling these. It's really kind of weird in terms of where electrons are filling. All right. But in the end, it's kind of useful. to just look at the periodic table and get an idea, generally speaking, of what it means. All right. So if I was looking at a periodic table, trying to get this periodic table back up here. All right. How is this useful to me or to you as a chemistry student if you're looking at the periodic table and you want to talk about bonding? All right. Well, the way it's useful is, let's say I ask you about a compound between, let's say, magnesium and sulfur. All right, that was a poor choice of colors because it didn't really do very well. Between magnesium and sulfur. Now, we talked about this last time. We said, okay, we know that magnesium is in group 2, so it's going to be +2. We know that sulfur is in this group, which we called, well, we called it a variety of things, right? But what I remember is we said, okay, anything in this group is -1, anything in here is -2, -3, that sort of thing. So we knew sulfur was going to be -2. We knew magnesium was going to be +2. We would know that that would form a compound Mg2S2, which is really MgS. So when we're doing the naming thing, that was relatively straightforward. What we didn't understand is, why is this +2? What's going on when magnesium is +2? Where are those electrons coming from? And where are they housed? And so what we're going to talk about, and we're out of time now, but we're going to talk about is, where are these electrons in magnesium? Where do they reside? And why is it just 2 electrons that like to come out and not all, well, I covered it up, but not all 12, right? Magnesium's got 12 electrons. Why does it only lose 2? Why doesn't it lose more, right? We didn't talk about the reason for that. So that'll be what we go to, and next we'll talk more in depth about bonding. Minsung was right. I did have some PowerPoints up, but I clearly did not use those today. We'll spend some time with those next time. Let me see if there's any questions. I don't see any questions. All right, I think I've kept you guys, well, 7:30. That's what time I usually let you go. Are there any other questions for me before we sign off for today?
No.
Professor?
Yes, Sammy.
Can you post last week lecture and today lecture on you?
Absolutely. I made a note to myself, and I will do it. What I'll also do is I will try to find a way to take these notes from my iPad and Notability and post them as well. I'm not going to promise that's going to happen, but I'm going to.
Actually, you can, when you press the share button, you can save as a PDF.
Yeah.
And you can just post on Titanium or
You're a man, Minsung. I'll give it my best shot, but I am an old guy, so if it doesn't happen right away, cut me a little slack, all right? Awesome. Anything else, guys? What I would recommend, actually, before I let you go, let me just share my screen one more time. What I might, why does that have to come up every time? What I might recommend, it doesn't even have me logged on anymore. I was going to go back to the class page. Where's my class page? This doesn't look like my normal portal page. It's kind of weird. I think I'm missing something here. Oh, that's why. Titanium faculty. Oh, again, it's probably going to make me log in again. Of course it is. I'm not on campus, so of course it wants to authenticate. Okay. We didn't have a chance to go there, but I would highly recommend that if you have some time, which maybe you do, that doesn't look right. If you have some time, which you probably do, I would say under resources, activities, and keys, this, I want to say it's this, let me double check. Yeah. So that last worksheet that I had posted up. It has some things about putting electrons in, doing electron configurations. We actually didn't get here quite yet. But if you did read ahead a little bit and talked about, okay, what does it mean by putting electrons in? And you can see kind of we've got this things written here. So 1s, 2s, 2p. And we're talking, we didn't talk about this particular picture about what these energy levels and orbitals look like. But if you did go ahead and read some of the reading and work on this, that might get you a little bit ahead for next time. But if you didn't do it, no worries. I'm sure you have enough time or enough things to practice with otherwise on homework. All right. So I'm going to stop the share. Are there any other questions? Awesome. All right. Well, remember, guys, email or send me a note, or you got my cell phone if you want to text me if you have any questions between now. We do not have a quiz or an exam this week. The earliest we would have an exam would be next week, Thursday. All right. So don't sweat that either. All right. Everybody good? All right. See you next week.
Thank you, Professor.
Bye, guys.
Bye, Professor.
Oh, wait, one other thing. If you wanted some points back on that quiz, send me an email as well and explain why you think you deserve more points. All right. Bye.
Good night, Professor.
Good night, guys. Good seeing y'all.